So, hello, this is the weekly report, I think, 4. I am testing out the contact as I have been. So, contact. And there I am doing a few things. Probably you know that I have done this system. Basically, the system is done. What has been left is the temperature, basically the control. That's not yet done. Something about the control. So the system is, let's say this is the quartz tubing, and here is the material. This is the, let's say, yeah, this is the quartz wool. So I need to heat this basically up to a temperature of 450 degrees, basically like roughly 450 C. And this is not that convenient as you may think, because yeah, you can try it out, and well, I'm going to explain the problem first. So this is like not that easy, because there are multiple problems. So I'm going to write this down. Problems. First of all, the heating element, I'm just going to draw it here. It's basically here. So I'm just going to star it there. It's there, but I didn't draw it to the sake of more clarity. So the problem is that as you heat up the heating element, there is like some thermal, I don't know, lag or delay. So thermal lag, we're gonna call it thermal lag. So the thermal lag is a bit tricky, because you might think that you heat this shit up and then it's going to immediately heat this up. No, it's not that simple. First of all, the thermal lag is what I mean by that is when I heat this shit up, it gets to a temperature, but it starts to radiate the heat around. So basically it is going to radiate the heat outside and inside. And even after I have turned this shit off, the inside temp will still go up, because this has not yet transferred its heat via radiation and through like transition, or how do you say this? So this thermal lag is kind of annoying, and basically I'm going to write here characteristic. So I'm going to write here characteristic. Characteristic. So the system via temperature looks like this. This is temp. This is real time. And basically, as you heat it up, the temp goes up. You turn it off here. So I'm going to draw under a time and input. So this is here. This is on. So this is on. This is off. So here we turn the temperature off, or the heating off, and the temp still goes on here. So this is so it still goes on and still goes up. It rises, then it will stagnate here a bit, then it will go down back again, and it does this, and you need to turn the heating on again here. So it's kinda, and it will lag here. So it is this, but it will still go down and it will go up again. It was maintain and so this is a bit annoying, because you can't really heat it up, and basically with these So here you wait. I call this the cooling wait. Cool wait. This is heating. So basically, here I am using a constant 10 second, and here it is like 28 sec, which I found like adequate. It still goes up over time, so the temperature with this little deviations looks like this. So from, let's say, it goes slowly but surely up, and it goes down and goes down basically, and it continues this trend. So this is kind of annoying because the temperature rises. As I said, the 450 C would be like ideal. Here it can go up as far as like, I don't know, 490, from like a 460, around 450, 460 to like 490, and it goes back. So with a variable time, I have been tinkering around, but I have thought about it, and this is only what I call the static environment. I will draw here. So I have separated out two typical conditions. The first one, let's call it static. Then I just use the regular system plus air. I don't use anything other than that. That's the system plus air. I can mimic the heating effect of the traveling air through the system, and the pressure because of the little jars. So basically, here are the jars. I'm going to draw a little tablet here. Wait. So here's the little jar. Here is the quartz tube. Here is the big jar. Here's the, basically this is the chamber. This is the bubbler. The bubbler has some water in there, which is going to create some static pressure above the pipe. Basically, this water level that is above the surface and the pipe's bottom. That's going to be slowing the system's air travel. Basically, if you were to pass just air through without any liquid in there, then you get the point that it would travel through faster, because there is like less friction, in that sense that, in the sense, friction is pressure basically, and the pressure doesn't let that much air out. Thus the pressure like reduces the speed, reduces the amount of air that can travel through, reducing the cooling that the air provides. So this is static. There is nothing really interesting about this. So in dynamic, I'm not going to write it out. So system sys plus SOx. So this is the sulfur oxides. This is a big X. So sulfur oxides, it can be like dioxide or sulfur monoxide, but it is mainly sulfur dioxide. So the sulfur oxides are a bit tricky in that sense that as they travel through the system that I have drawn previously, I'm going to put you closer, that I have done previously, the problem is that the SOx reacts here at the catalyst bed through the catalyst, and it generates heat. It generates heat through the thermal, through the chemical reaction. It generates heat, and that's going to impact our system's characteristic in both that when we look back here, this is not going to be 490. This is, I didn't try it out yet, but this is going to be like 510 or maybe even more, because the system will get more heat in, And the static things, the static basically constants, 10 seconds, 28 seconds, or you can name whatever number you want there, that's not going to be adequate here because it is not going to be the same. But you might ask, why don't you just test out the dynamic system waiting times and then call it good enough? I could do that, but there is another problem with that, because when we do that, if here the sulfur that is being burned, that can vary in the amount, basically depending on like temperature, how well I heated the thing up, because as you know, sulfur doesn't really burn at ambient temperature, at room temp. It tends to burn when it is liquid, or at least around 100 degrees Celsius. It likes to be heated up before it starts to liquefy, then it can be lit. The problem with that is that it can change how much sulfur I burn, and basically the concentration of sulfur dioxide in the mixture dictate how much heat is produced. So this is not constant. This depends on time, temperature, moisture level. This can change every single day. If the humidity in the basement that I am working in changes, then so can the concentration of sulfur that I will be burning, even with the same conditions, given heat and all that stuff. So that can impact the system's heat that has been generated from the sulfur reaction, the chemical reaction on the catalyst. So this is like vanadium pentoxide, V2O5, plus the, sorry for the ugly writing, V2O5 plus the SOX, but mainly SO2. So this is reacting here that generate heat, and when this SOX basically sucks, is lower in concentration, this is less with the amount of air that is being pumped in there. That means that the heat will change, and that means that the temperature will drop compared to the higher concentration, and so can be with higher concentration the temperature can go up. And we want to maintain this 450 dash like 470 degrees, or maybe even we can go down to like 430. So for this 40 or 30 degrees range, we want to maintain this, because this means that we are generating more. This is SO3, so this is generated from this. So this SO3 is generated, but the problem is that with higher temps it can go and turn back into SO2, which is not that good for us. With higher temps this can redox and get converted back into the SO2 version, which is not good, because the water that is used to capture the sulfur trioxide is not going to react with the sulfur dioxide. Sulfur dioxide really doesn't like to react with anything. It just goes out the fucking window when we convert it back, or not we, the system converts it back. The vanadium pentoxide can act as a redox agent in here, so that's not really what we want. So we want to maintain lower temps for this, sorry. So we want to maintain lower temps, so 450, so 430, 470 degrees even. That would be like something to look for. And now there is the alternative, the better version of this system approach or analytics, that we measure the system's, I'm just going to draw here, system's temperature with time. It goes up like something like this, then it goes down, it goes, and it looks something like this. Of course there are like little deviations here, like it looks like here if you zoom in, but it doesn't matter. So this is this, and we, with a lot of data that we collect, we can plot this out into this little nice line, we can then turn this and fit a polynomial over it. So as you have seen, I will just draw it out. This looks like this. Then we can create a mathematical like system model, I would say. So mathematical system model, MSM, and we can use that to like predict the temperature and all this stuff, and we can use a controlling mechanism, a controlling model. We can create a GS, like the transfer. We basically with these plots we can create functions. These are functions with basically they can create a internal temp. So I'm going to explain it right quickly. So I have measured that you could see there is like a outside temperature probe. I'm going to throw it right here. So here's the quartz tube. This is like rock wool around it, and this is the band. The band has a thermocouple connected to it, but this pipe that connects to the end of the quartz wool, this is the quartz wool, quartz tube. This is the silicone pipe. The silicone pipe has a sneaked in thermocouple that has been, this is the thermocouple, has been led into the quartz wool, and it can measure. This is like siliconed in. So this is the temperature probe, and this is the inside. So this is the temperature probe. This is the inside the quartz wool. This temperature probe directly measures basically the inside temperature, and here the external, the outside boundary closer to the exit. And I measure this with a multimeter. So here's my multimeter, and here basically multimeter, and here I can connect this to the Arduino. So the Arduino reads the external temperature. We know I measured the time with my phone or something like that, and I have basically logging to a piece of paper the internal temperature, and I have basically as these internal temperatures I have plotted out, created the mathematical system model. I have created a transfer function with MATLAB, and then with these I can create a kind of control system, control that can adjust itself and can vary these waiting times and the heating times. Of course, I'm going to put a boundary condition to both, to a minimum and maximum amount that it can wait and it can heat, because I have came up with this. It went for like 33 minutes, and it like for no okay, it went, the temperature, inside temperature went down, and it found out that now I'm going to turn it on for like 40 seconds, and it heated the shit out of the pipe. So I just needed to basically, I didn't even need to turn it off, but you get the point. From like 430 degrees it went up to like 600, so it was a bit overshoot. So I just need to fix that. But so I'm creating a control. The control is going to vary and adjust the temperature or the waiting times and the heating times dynamically in the system. So if I do this, so if I do this to the static environment, then the dynamic will be a bit easier also, because this, if the static works well, then the dynamic will also. Of course, with the dynamic, you can say that there will be the heat gradient and all this nonlinear bullshit come up, but that's a problem for another day. But this system, the control, if I fine tune it, then it will be able, basically I will be able to adjust it to and tailor it to this dynamic system more easily if I have the right dynamics. I will need to fine tune it a little more from the static to the dynamic, but if I understand the system better, then it will be easier than just going in straight into the dynamic and sucking with that, and also like coming up with like static constant numbers. It's not going to work, of course. So this is what I have been up, and this is what I have been doing. Probably going to do a more like material view. Basically, I'm going to take you to the basement and show you this system, but you have seen the system. It's not that interesting to see that. This is more interesting, and basically the logic behind it that required to basically do this, and with a great efficiency, because as I said again, we need to maintain this temperature, I mean roughly plus or minus 10 or 20 degrees. That would be optimal to our system, because we will probably lose a lot of product through this water bubbling through bullshit. I'm going to do a peristaltic pump and spray nozzle design with that, but like for now this is like good enough. It could be improved in the future, what I want to say. So this is for now. If you enjoyed it, make sure that you like and subscribe and all this comment, whatever bullshit. It's cringe to us, because I always say, but it helps to drive the algorithm up. And yeah, thanks for watching. If you found it, make sure you watch the next episode, because we will be coming back, and guess what, we'll do more maths and more chemistry. So without further ado, that was for today. See you in the next one. Peace. Do the hard work, especially when you don't feel like it. Mwah.